morning. Good morning, Adnan.
Good morning, ma'am. How are you?
Good morning, Samuel.
Hi, teacher.
Good morning, Samuel.
Buenos días, don.
You can start the class, Adnan.
Okay, thank you very much.
Guys,
Okay.
enjoy the class and pay attention, okay?
Okay, I hope my screen is visible. Welcome to the chemistry class, students, and good morning. Okay, so today we will discuss three topics. For the first one is complex chemistry, and the second one is radicals, and the third one is isomers. All these topics are very important in terms of chemistry, and they have many different applications in different industries, in healthcare, in the industry of paints and medicine. So we will look at these three topics today. So we are starting from complex chemistry. What is a complex chemistry? Complex chemistry, the word complex, it doesn't mean that this is very difficult. Normally, when we say that something is very complex in English, so we do not say it. We do not mean that this is very difficult. In chemistry, a complex chemistry is chemistry of transition metals, right? So what are transition metals? If you look here, so we have this D block in the periodic table, which is mentioned in the blue color, right? So all the metals, all the elements that we have here in the blue area, so these are called transition metals. So whenever these metals, they form the different compounds, those compounds are called complex compounds, right? So again, when I say, or when we study complex chemistry, we doesn't mean that this chemistry is difficult. I hope this point is clear, right? So what are coordination compounds, or what are complex compounds? So complex compounds are mostly formed by D block elements, just like we studied right now. I showed you the D block. You can see here the blue color, this is D block, right? So we have different types of elements in this section of the periodic table. For example, we have iron here, we have cobalt here, we have copper, we have aluminum, we have gold. So all the important elements that we normally use in our chemistry, so they are included in this family of the periodic table. So coordination compounds are complexes of metal ions and which have one or more ligands, right? So mark this word. So this word is important in order to understand the basics of coordination chemistry. And I will ask you about this. So pay attention and be attentive, and try to be engaging and responsive as much as possible. So the metal acts as a Lewis acid, and the ligands acts as a Lewis bases. So coordination compounds have distinctive properties such as color, magnetic behavior, and reactivity. So as I said, that these compounds are very important in terms of an industrial point of view, for whether it's a paint industry or a healthcare industry, right? So all the garments, the clothes that are used for paint, right? For example, I have this piece of cloth here. Let me show you. So as you can see here, that this is a red flower, right? So the paint that has been used here, this is from the coordination compound, okay? So this is how coordination compounds are used in daily life. So now we are talking about the structure and bonding of the coordination compounds. So coordination compounds can have a different coordination numbers and geometries, right? So whenever we say that it's something about a coordination number or a geometry, we talk about a specific shape in our mind, right? For example, if I ask you to imagine a cube, so you will imagine a box-like shape, right? So for example, if I ask you to imagine a circle, so you will imagine a ball, a football or something, right? A sphere. So this is how the angles and the geometries of these molecules, it works. So the coordination number is the number of ligands attached to the metal ion. So shortly, we will look at the structure of the coordination compound. In the center, we have the transition element, we have the transition metal, and on the sides, we have ligands, right? So in different coordination compounds, we can have different types of ligands. I will explain that shortly. You will see in the picture. So the coordination geometry is a spatial arrangement of the ligands around the metal ion. So in the geometry, we talk about that how many atoms or molecules or groups of atoms, they are arranged around that central metal atom, and what are their angles, what is the final shape of the molecule, okay? So examples of coordination geometries include, so the shapes can be octahedral, tetrahedral, and square planar, etc., right? So for now, we can remember these three types of shapes: octahedral, and the second one is tetrahedral, and the third one is square planar. So if I ask you that what are coordination compounds, so what will you say? You will say that coordination compounds are those compounds which are complex compounds formed by the D block elements, for example, cobalt, aluminum, copper, gold, etc. I hope this point is clear. So now let me show you this picture of a complex compound or a coordination compound. So don't get scared. It's a big compound, but it's very easy to learn and understand. So as you can see here, that we have cobalt in the center. I hope you can see this CO. Let me maximize this for you. Let me enlarge the picture. Okay, so as you can see here, that this CO at the center, this is from the D block and the transition metal. This element is from the D block element, okay? So if you have the periodic table, you can check the periodic table and you will find it somewhere here, okay? In the middle of the periodic table, which we call D block. And this entire molecule, this is basically a complex molecule, and we call this a coordination molecule, okay? And these are the pictures, octahedron and tetragonal elongation we have here. Here we have an example, and you can see we have another picture, tetragonal compression. So these are the different shapes that we have in coordination compounds. So I hope we are clear so far. If you have any questions, you can ask. Do we have any questions? Samuel? Are we clear?
Guys, it's clear for you. If you have some question, you can turn the phone and ask directly to the teacher, okay?
It's clear, teacher.
Okay. So in the coordination compounds, I asked you guys to pay attention on the term ligands, okay? So how do we pronounce this? ligands. It's ligands, Ligands. So what are the ligands? So ligands are molecules or ions that bond to a central metal ion. So if you can see here in this picture, let me maximize it for you here. So here in the middle, we have copper, and on the sides, we have water, right? We have H2O, 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 H2O. So all these group of molecules or group of atoms that you can see in red color, these are ligands. So can anyone tell me that how many ligands do we have are attached to this molecule? Facundo, I hope I'm pronouncing your name properly. Can you please tell me that how many ligands do we have here attached to this molecule? Samuel? Yes, Facundo, please. I can't hear you. Can you please speak a little bit louder?
How many what?
How many ligands do we have are attached in this molecule with copper? You just have to count the red ones.
Okay. 6.
How many?
6.
6. Did you say 6?
Yeah.
Okay, excellent. Yes. So we have 6 ligands attached to this central metal atom here in this compound. Excellent. So Samuel, can you tell me how many do we have here with copper in this one?
We have 6.
Yes. So we have 6 fluorine or fluorides attached with the central copper, and the copper is from the D block. So and what do we call these 6 atoms? Ligands, right? These are ligands. Okay, so I hope this point is clear. So now let's move forward. So ligands are molecules or ions that bond to a central metal ion. Okay, so we just saw in the picture, and you guys calculated it, and you guys answered the question. It was correct. That's very good. So common ligands include water, ammonia, and chloride ions. So mostly in terms of ligands, we will have water, we will have ammonia, and we will have chloride ions. So ligands can be classified as monodentate, one bond to the metal atom, or polydentate, multiple bonds to the metal atom. So what do we mean by monodentate and polydentate? So that means that sometimes we will have ligands that this one ligand will be forming 2 bonds. Here you can see that water is making 1 bond with copper, and here you can see that fluorine or the fluoride ion is making 1 bond, and there is 1 line, right, with the copper. So this is a monodentate. Mono means 1. Always remember that mono means 1. And whenever we have more than 1, we can call it bi or di. If we have 3, we call it tri, right? If we have 4, we call it tetra. If we have 5, we call that penta. So you need to remember this terminology in order to learn different types of things. So this is very important in other subjects as well. It will help you there. So monodentate are those ligands that can make only 1 bond with the central atom. And you can see here it is written 1 bond to the central metal atom. Okay, and polydentate, multiple bonds. It means more than 1. It can be 2, it can be 3, it can be 4, and so on. Okay, so I hope this point is clear. ligands can have different types. What are those types? We discussed two types, monodentate and polydentate. And the term, this word dentate, this came from the teeth, okay? So in Greek language, the teeth are called dentate. So I hope this point is clear. Now you will remember it. So, and we have chelating ligands are polydentate ligands that form a ring structure with the metal ion. So as you can see here in this picture, these are chelating agents. They have formed ring shapes. We have rings here in this picture, in this molecule. So the molecules that are attached here are in ring shaped. So you can see here, this is cobalt, and this entire ligand, it has formed two bonds. Okay, so one nitrogen from this side and the other nitrogen from this side. So we will call this a polydentate ligand, or we will call it a bidentate ligand. So I hope this point is clear, and we can safely move to our next slide. So here is again a summary of what we have studied so far. You can see that in the transition metal complexes, we have a central metal atom, you can see M, and then we have L. Okay, so we have 6 different ligands attached to this central metal atom. And this central metal atom, it will always be from the transition metal center, okay? And transition metals are found in the D block of the periodic table. So I'm repeating this again and again for you so that you can understand it properly. And if you have any questions, you can please ask, okay? So here we can have copper, here we can have, and we have cobalt, here we can have iron, okay? So most of the transition metals, they can come here. So, okay, so here is another picture of the transition metal complexes, and you can see here in the center we have iron, Fe, ferric or ferrous. We call it ferric or ferrous in chemistry. This is iron, and this Cu stands for copper. So I hope you must be familiar with the names of the atoms and the symbols of the atoms. So Cu stands for copper. So these both atoms, these both elements, they are from the transition metals from D block of the periodic table. If you have a periodic table with you at the moment, or you can check from your book, so you will find these two in the D block of the periodic table. And you can see here that how many different ligands are attached: 1, 2, 3, 4, 5, and 6. So we have 6 ligands, and these are H2O, water. So here's the formula for this transition metal complex. You can see here, there's 6 here. You can see here, 6 is written here. So that means 6 water molecules are attached to this iron central metal ion. Here with the copper, we have 2 different types of ligands. So here we have water, H2O. Here we have water, H2O. So we have 2 waters attached to copper, and we have 4 ammonia molecules. So you can see here in the center we have copper. So we have written it like this, Cu. And again, after that we have ammonia, and then we have water. So we have 4 ammonia molecules attached to copper, and then we have 2 water molecules attached with copper. So, and the total charge on this molecule is 2 plus, and the charge on this molecule is 3 plus. So I hope this is clear. And these are called ligands, and you can see here that they have formed only one bond. So that is why these are called monodentate ligands. So now we will discuss isomerism. What is isomerism? It is basically the same chemical formula but different structure, right? So in chemistry, we can have different molecules that have the same molecular formula but different arrangement in space, how the atoms are connected to each other, that is different between the two molecules. So coordination isomers have the same empirical formula, but different ligands attached to the metal ion. Okay, so if you look here in this example, this is cobalt, right? CO, this is C, and this is O, cobalt. So we here after with cobalt we have ammonia, and how many ammonia molecules do we have? 5. And after that we have chlorine, and now the parenthesis has been closed, and sulfate SO4 is outside the bracket, right? If you look here, so Cl is inside the bracket, chlorine is inside the bracket, and SO4 sulfate is outside the bracket. But here in this molecule, the chlorine has been replaced by sulfate SO4, and chlorine is outside the bracket. Okay, so I hope this point is clear. So if you count the number of atoms in both these two molecules, they will be the same. If you count the types of the atoms, they will also be the same, but the way they are attached to each other, that is different, and that means that these two compounds are different compounds, and we call them isomers. Okay, so let me repeat it again. What are isomers? Isomers are basically compounds that have the same molecular formula but different structural formula. Okay, different attachment in space. So coordination isomers have different physical and chemical properties due to the different ligands attached to the metal ion. So here chlorine was attached to cobalt, here sulfate is attached to cobalt. So here is an example. You can see here in this molecule that look at the formula here, right? So Cl is written inside the bracket. So Cl is attached to cobalt here, and the bromine is outside. Bromine is not connected to the cobalt. Okay, and how many different ligands do we have here? We have 6. It is not always 6, remember that. Okay, it is just the examples that you are seeing 6 different ligands, right? We have ammonia, we have 5 ammonia molecules, and we have 1 chloride. But here, if you look at this molecule on the right hand side, you will see that bromide is connected to the cobalt. It is inside now, and the chloride molecule is outside. Okay, so I hope this point is clear. So these two are called isomers. We will study this in our lecture in detail in the upcoming slides. So what is a geometric isomerism? Okay, so this is a type of isomerism in the coordination compounds that we see that in which we see that the different arrangement of the atoms in terms of the angles. Okay, so this like for example geometry, if I ask you to imagine a shape like a tetrahedral shape or a cubic structure or a circular structure, so different geometric shapes will come to your mind. Okay, so this is the type of isomerism that we usually see in this type. So geometric isomers have the same molecular formula but different spatial arrangements of the atoms. So cis-trans isomerism is a type of geometric isomerism that occurs in coordination compounds with 2 ligands of the same type. So for example, we have cobalt, we have ammonia, and we have chlorine. You can see here has 2 geometric isomers. One is called cis and the CIS, and the other one is called trans. Okay, has 2 geometric isomers, cis and trans. Optical isomerism is another type of geometric isomerism that occurs in coordination compounds with a chiral ligand. Okay, so look here, we have two different types. And as you can see here, we have a central cobalt atom in the middle. And look at here on the left hand side, chlorides are attached here on this side. So this is called cis. And here in this side, in this molecule, and the chlorides are attached on this side. So this one is cis, and this one is trans, trans. Okay, so I hope geometric isomerism of the coordination compound is clear. So for this topic, we have 2 slides left, and then we will move to radicals. Okay, so another property of the complex chemistry or the coordination compounds that we need to study is, in the beginning, I told you guys that the complex compounds or the coordination compounds are very important in terms of colors. So if you look here, like I gave you the example of the red color. So now I have this here color. So you can see here that it is blue. Okay. So what happens is when we have a blue color, so when the light is absorbed in the cloth, so what will happen? Look here, blue. Okay. So this compound is used in this color. Okay. So in this molecule, we have a blue color. So here, this is the compound that has been used. So all the coordination compounds or the complex compounds, they form different colors. Okay. So for example, if you are wearing a shirt, if you are wearing a blue shirt, that means that this compound is a part of your shirt. Okay. For example, if you're wearing a blue jeans, so most probably this compound will be used during the process of coloring your jeans. Okay, of your pants. So we have yellow at 535, we have 500 and blue green. We have at 475 nanometers of wavelength, we have blue. We have 310, we have ultraviolet. We have at 600 nanometers, we have red. And at 498, we have blue green. Okay. And these are all the different colors. When we combine them, you can see different types of colors. So this is why I told you guys that these compounds are important when we talk about the colors or different types of things. So the applications of coordination compounds. Coordination compounds have many practical applications, such as in catalysis and medicine. Okay, so what is catalysis? Anyone? Do you guys know? It means to speed up. Okay, to speed up the reaction. So these coordination compounds are used with other reactions when we need to speed up those reactions. Okay, so remember this point that the coordination compounds can be used when you want to speed up different reactions, when you will go to the university, when you will be doing research, when you will be a scientist and making something. So there you will use these coordination compounds, where you will use these compounds to speed up the reactions. Okay. So one example of the coordination compound used in medicine is cisplatin. So cisplatin is a compound which is used to treat certain types of cancer. Okay. So cancer is a major health issue nowadays. And we have different types of cancers. We have many patients dying of cancer each year. So if you want to treat cancer, these compounds can help you. So coordination compounds can also be used as dyes and pigments, such as the blue color of many laundry detergents. So I just showed you the blue color. So this was all about the coordination compounds. And now we are moving on towards the second theme of today's lecture, which is radicals. Okay, so I hope everything is clear for the complex chemistry, the coordination chemistry. Don't worry about the name. It is not complex. It is not complicated. It is very easy. It is just the name. Okay. So we call it coordination compounds. So introduction to radicals. So what are radicals? Let's see. Do you have any idea, Samuel? Do you know what are radicals? Facundo? Any idea about radicals? Okay, let me explain. Yes, Facundo, I can see you unmuted your mic. Please participate in the class.
No idea, sir.
Okay. Please pay attention so that you can learn this important concept. I will ask you in the end again. Okay, so I need your attention here, complete focus. So radicals are molecules or atoms with unpaired electron. So this is the simplest definition that you need to remember if you want to define radicals. Okay, so what are radicals? So radicals are molecules or atoms with an unpaired electron. So anything, any atom or molecule, if it has an unpaired electron, so that species will be called a radical. So radicals are highly reactive and can participate in many chemical reactions. These are species that are highly reactive. That means that they can react violently, they can destructively. Okay, so um, let's look at their properties. How do we denote them? Examples of radicals include the hydroxyl radical OH. So and here dot. So you can see this. It is a dot, and whenever we want to represent a radical, we put this dot on the right hand side in the center. So I hope this point is clear. And the methyl radical CH3. So what is CH4? It is a methane gas that we use in our homes to cook. When you turn on your stove, if you have a gas stove, nowadays we have electric appliances, we have electric stoves. We just turn on the button, we put on the kettle, and we make tea or coffee. But sometimes in some countries where people use stoves with gas, and they have to turn on the fire. So that gas is basically, most of the times it is methane, and the formula is CH4. So if you remove one hydrogen from methane, so you get CH3, and that CH3 will be turned into a methyl radical. So I hope this point is clear. So what are radicals? Radicals are molecules or atoms with an unpaired electron. So can you define radical now? Fikandu, can you define what is a radical?
Mm,
It's okay, it's okay, please try. You can just read the first line.
okay, radicals are molecules or atoms with an unpaired electron.
Yes, excellent, with unpaired electron. Okay, I hope Samuel, you are with us and you are also paying attention. So good job, Facundo, thank you. Okay, so now we are moving towards our next slide, formation of radicals. So now we will look at the formation, that how the radicals are formed. So let's study this. So radicals can be formed by homolytic cleavage. Okay, what is a homolytic cleavage? This is the term that you need to understand. Homolytic cleavage. Homo means same, and lytic means to break down. Okay, what do we mean by homolytic? Homo means same, and lytic, L-Y-T-I-C, it means to break down, and cleavage, separation. When something is separated, we call that a cleavage. So which occurs when a bond is broken and each atom retains one of the two electrons in the bond. And radical reactions are chemical reactions that involve the formation or a reaction of radicals. So one example of a radical reaction is the combustion of methane. So what is the combustion of methane? When the CH4 burns in the absence or in the presence of oxygen, okay, it will produce CO2 and H2O. Okay, and in this reaction, sometimes CH3 will also be produced. That is called the incomplete burning of the methane gas. So stability of the radicals. So let us talk about the stability. So how stable these molecules can be. Stability is basically the opposite of reactivity, right? When we say something is very reactive, the opposite of it is something is very stable. Molecule A is highly reactive, molecule B is highly stable. Stability means when something does not react. It does not need to react with other atoms. So when we say that this molecule is stable, that means that this molecule will not react. For example, gold. You may have seen gold, women, they really like it. They wear it as a jewelry, the rings, or like around their neck in chains, right? Males also wear gold and diamonds. So they are highly stable, they do not react, okay? The stability of the radicals depends on factors such as resonance, stabilization, and delocalization of the unpaired electrons. So what is resonance stabilization? Resonance stabilization is where when charge is distributed over the entire molecule, okay? I would suggest that you guys should have a paper and pen with you. So whenever I explain something, you can note it down, okay? So the important terms that I explained during the class, you guys can note it down with you so that you can revise later and you don't forget them. So radicals can also be stabilized by the presence of electron donating or electron withdrawing groups. Radicals can also be stabilized by the presence of electron donating. What do we mean by electron donating? Those atoms that have many electrons, and it can share those electrons with the other groups, or electron withdrawing. So what do we mean by withdrawing? Those groups that can take electrons, okay? So for example, someone who has lots of money, so we will say that he is a donating person, or someone who is charitable, who is giving his money to the charity, we will say that he is money donating person, and someone who accepts that money, we will call that money withdrawing person, okay? So he's accepting that money. So I hope the electron donating and electron withdrawing concept is clear. For example, the benzyl radical, okay? So here we have the example of radical. And what is the formula? C6H5CH2, and then we have a dot. So if you remember, I told you in the beginning, so that when we want to draw or write the formula of a radical, we always put this dot at the end. And what does this dot represent? This represents the unpaired electron, okay? So when I defined, if you look at the definition here, the unpaired electron. So this word, so by this dot, we represent this. What is this? Unpaired electron, okay? What is this? This is an unpaired electron. So all the radicals, they will have this unpaired electron. That makes it a radical, okay? So this makes this entire molecule a radical. If you remove this, you will have to add another hydrogen. How many hydrogens do we have here? 2. You will change it with 3. Now this is not a radical, this is a complete molecule. But if you want to make it a radical, so you have to remove 1 hydrogen, and then you have to put a dot. So is stabilized by the resonance effect of the benzene ring. So this is benzene ring C6H5, and here the charge is distributed. So let us talk about the reactions of some radicals. So radicals can participate in a variety of reactions, including addition, subtraction, and substitution reactions. So what is an addition reaction? What will happen in the addition reaction? It is very simple. Different atoms will be added. What is a abstraction? Okay, so a molecule will be lost, an atom will be lost. And what is a substitution? If you guys enjoy watching football, you will be familiar with the word substitution, right? One player is called back from the field and another was sent. If you remember the World Cup final, Cristiano Ronaldo was sitting as a substitute in the beginning, right? So he was waiting for his turn. So this is what a substitution means. So radical addition reactions involve the addition of radical to a double or triple bond. So here is the radical reaction. This is an ethene molecule. You can see here we have a double bond. And what is happening here, that the double bond, MP, okay, thank you. So the double bond has been converted to a single bond. And what happens here, that the entire molecule will be converted. And this reaction is very important for the plastic manufacture, plastic bottles, the plastic phone covers, right? So all the things that we use for plastics, this reaction is used. And what is happening in this reaction? Basically, a radical reaction. I hope it is clear. Any questions? Do we have any questions?
No, teacher, is clear.
No.
Okay, thank you. So radical substitution reaction, I told you to you guys about the substitution reaction, that what happens in a substitution reaction, one atom is added and the other one is called back. So here, radical substitution reactions involve the substitution of a hydrogen atom with a radical. So you can see here that it was CH4, and now here you can see that it is CH3 with this unpaired electron. Okay, what happened? This is a chlorine radical or a chloride radical. It attacked this molecule, it collided with this molecule methane, and when it collided, when it attacked this molecule, so it ejected one hydrogen, and instead of, and while removing one hydrogen, this unpaired electron has been shifted to methane, okay? So I hope this point is very clear. This is called the substitution reaction. So now what are the applications of radicals? Radicals have many practical applications, such as polymerization. What do we mean by polymerization? Polymerization is a chain reaction, okay? When different molecules, they react with each other and they form long chains. We call that polymerization reaction. I hope you guys are paying attention. You can note it down. I hope you will have a pen and paper with you. So polymerization reaction, what is a polymerization reaction? Chain reaction, okay? When different molecules, they react with each other and they form different long chains. So one example of the radical-based polymerization is the free radical polymerization of styrene to form polystyrene. What is a polystyrene? It is a form of plastic. Whenever you go to Starbucks to drink your coffee, the Starbucks cup is made of this material, polystyrene. And how do they make this this cup? It is with the help of the radical reaction, and the name of the reaction is polymerization reaction. Okay. Radicals can also be used in organic synthesis to form new carbon-carbon and carbon heteroatom bonds. So this was all about radicals. So now we have 15 minutes left in the class, and now we are moving towards our final topic, the third topic for today, and that is isomers. So we talked about isomers when I was discussing the complex chemistry and the bonding and the coordination compounds. So what are isomers? Isomers are basically molecules that have the same molecular formula but different structural formula. Okay, so now we will discuss the isomers here in a little bit detail, and I will explain that how many types do we have of isomers. And this is also very important in terms of research. One compound will be poison and the other compound will be a medicine, but they will all have the same atoms, same number of atoms, but they will be connected in different arrangement. Their arrangement will be different, and the different arrangement will impart such a huge impact on the properties that one molecule will be a poison and the other molecule will be a medicine. So isomers, what introduction to isomers? Isomers are molecules with the same molecular formula but different arrangement of atoms. So MP, Facundo, Samuel, if anyone asks you to define isomerism, so you need to remember this definition. Okay, you can note it down. Isomers are molecules with the same molecular formula, but with different arrangement of atoms. This is very important. Okay, so isomers can be classified as structural isomers. Now we are looking at the different types of isomers. We have structural isomers, we have stereoisomers, or we have conformational isomers. Okay, so initially we will talk about these three different types of isomers. So structural isomers have different connectivity between atoms, while stereoisomers have different connectivity but differ in the spatial arrangement of atoms. I will explain that what these terms they mean. At the moment, you just need to remember the terms structural isomers, stereoisomers, and conformational isomers. You need to understand these three terms. So structural isomers have different bonding patterns and molecular forms. For example, pentane and 2-methyl butane are the structural isomers. Structural isomers have different physical and chemical properties and due to their different bonding patterns. So let me show you a picture of the structural isomers. Any questions so far?
Guys, is clear? Is
Yes,
clear?
teacher, is clear.
Okay, thank you. You can continue, teacher.
So here in this picture, you can see that these two compounds, they are isomers of each other. They are structural isomers of each other. And you can see here that how many carbon atoms do we have? 1, 2, 3, 4. And how many hydrogen atoms do we have? We have 10 hydrogen atoms, 4 on top, 4 at the bottom, and 2 on the sides, 10. But look at the structure of this molecule. This has a straight chain, right? And the other molecule, it has a different structure, right? The carbon is attached to the central atom. Isko andar le jao. Okay, so now we have stereoisomers. So what is a stereoisomers? Stereoisomers have a different molecular formula and connectivity, but differ in the spatial arrangement of atoms. So enantiomers are a type of stereoisomer that are non-superimposable mirror images of each other. Chiral molecules have an asymmetric carbon, and it can exist as a pair of enantiomers. I hope this point is clear. Let me show you another picture from the stereoisomers. So here is a picture of the stereoisomerism. And if you look at the compounds here, that on the left hand side we have two groups attached on the top, and here on the right hand side we have these atoms. They are attached across the molecule, right? So we have methyl here, we have methyl here, and this is the double bond, and now they are attached across. So this was the cis-trans isomerism example. So conformational isomers are stereoisomers that differ in the rotation of around the single bond. Okay, so the different conformations are often represented as Newman projections. One example of the conformational isomer is butane, which can exist in the staggered or eclipsed conformation. So this is another type of isomerism. Here we have a conformational isomers, and yeah, so this one can be best explained by a picture. Let me show you the picture of a conformational isomerism. It is just like the eclipse. So I think this picture is relevant. So let me paste it here. Okay, so in this picture, if you look at these two molecules, so what is happening that here we have CH3, we have a carbon, and here we have three different hydrogens. And here we have another carbon, and the three different hydrogens are attached here. So if you look at from this side view, for example, if you have a plastic bottle, and if you want to look at in the plastic bottle from this side, right? So what you will look, this molecule will look something like this. Okay, so here you can see that here is the first carbon, and the second carbon is behind this another carbon. So here is another view, and here you can see that this is the eclipsed form, and this is the staggered ethane. So two different terms are used to explain these two molecules: staggered ethane and eclipsed ethane. Okay, so I hope this point is clear. Cis-trans isomers. What is a cis-trans isomerism, or what are cis-trans isomers? Cis-trans isomers are basically around the double bond. We will have a double bond in the middle, and the atoms are arranged in different types around that double bond. And then finally, we have optical isomerism. Optical isomers are enantiomers that rotate plane polarized light in opposite directions. For example, if you have two different let's say optical isomers that are optically active. So if you dissolve them in a glass, so and if you pass the light, so one molecule will rotate that light in a clockwise direction, and the other glass will rotate that light in the in anti-clockwise direction. So we use plus and minus signs for the rotation of the light. Optical isomers have identical physical and chemical properties except for their interaction with plane polarized light. So optical isomers have identical physical and chemical properties, but the way they interact with light, that is different, okay? So this was about the optical isomers. Now, finally, we are moving towards the application, okay? So here in terms of application, isomers have many practical applications such as drug development and flavor chemistry. For example, if you have a molecule which is isomer, it will have a sour taste, and the other isomer of the same molecule will have a sweet taste with the same molecular formula, the same number of atoms and all that. So one example of the importance of stereochemistry in drug development, this is the example, thalidomide, okay? So you need to remember, for example, if during exam they ask you to present the example of the drug which uses isomerism, so you can say that thalidomide is the drug that is based on isomerism, which caused birth defects in one enantiomer but has therapeutic effects in other enantiomer. So this drug thalidomide, the one type of isomer of the thalidomide is dangerous. It can cause birth defects, and the other enantiomer of this molecule, it has therapeutic effects. It can be used as a medicine. So isomers can also affect the flavor of food and beverages, such as different isomers, carvone and spearmint. So when you chew on a bubble gum or a chewing gum, or simply gum that mostly teenagers they like, so the flavor that comes in that gum is carvone. So this is also an isomer of a compound. So this was today's presentation. We covered 3 different topics. The first one was isomerism, the coordination chemistry, the complex chemistry. And the second one was radicals, and the third one was isomers and its types in detail. So if you have any questions, please ask. You have 2 minutes. Otherwise, we will conclude the class.
Guys, everything is clear because the class going to be closed in 2 minutes. If you have some questions, you can turn your phone and ask directly to the teacher.
I think it's clear, teacher.
Okay, so no questions. Yes, ma'am, this was all from my side.
Okay, excellent class, Adnan. Congratulations. Thank you guys for being here, and remember to be planning for next class. Okay, your schedule. Have a wonderful day to all of you guys, and enjoy the rest of the day. Thank you, Adnan.
Thank you so much. You're welcome.
Bye, teacher.
Bye, guys. Bye, Samuel.
Bye,
Facundo.
Samuel.